In this video, I'll start with the steps to finding the probability of an event. So the first thing you want to do when you want to find the probability of some event in an experiment is, first of all, set up the appropriate sample space S for the experiment. In other words, determine what set's going to represent all possibilities that can occur during your experiment. And then number two, assign acceptable probabilities to those simple events in S. Now, when you assign those probabilities, you can use theoretical probabilities or empirical probabilities depending on the experiment, and I'll show you that in a moment. The other thing is, to obtain the probability of some arbitrary event E, you simply add the probabilities of the simple events. Now, if the probabilities of the simple events are all equal, then this problem is actually easier to do than what one might think. So for instance, let's do one that does have the equally likely scenario in it. Suppose we roll a pair of fair six-sided die and we want to observe their sum. Now, we'll let the sample space be the set of 36 possible rolls that I previously showed you. Now, let's assume that each event is equally likely to occur. So we'll assume that the probability of any random simple event has a probability of 1 out of 36. So now, let's say that we wanted to know the probability of rolling a sum of 5. Well, let's take a look at the event space for rolling a sum of 5. The event space would be the roll of 1 and a 4, 4 and a 1, a 2 and a 3, or a 3 and a 2. And so you can see there's 4 possibilities. And each one of those possibilities has a probability of 1 out of 36. So if we add each of those up, we'll actually get 4 out of 36, which reduces to 1/9. Now, in a moment, we're going to find out that we can do this even simpler because since these events, each of these simple events are equally likely to occur, we can actually calculate the probability of this event by just figuring out how many elements are in the event space. And you can see up here there's 4, 1, 4, 4, 1, 2, 3, and 3, 2. And then divided by the number of elements in the sample space, which there are 36. So 4 out of 36. So in the equally likely scenario, you don't actually have to add all of these equally likely events together. You just count how many of them there are. So that leads me to this equally likely assumption. And so the equally likely assumption, it means that all events will have the same probability. So if there are n simple events, then each simple event will have probability 1 divided by n. So just like if there were 10 names dropped in a hat and you wanted to know the probability of selecting a random person from the hat, since there's 10 names in the hat, the probability would be 1 out of 10 for each person. And now this is a theoretical probability. And so by using this equally likely assumption, we can state that the probability of your event is simply the number of ways to get the event over the total number of outcomes possible. So again, if you go back up here to the probability of rolling a sum of 5, you'll notice that there were 4 ways to roll a sum of 5, and there was 36 possible rolls total, so the probability was 4 out of 36. Again, that's because each of the simple events were equally likely. Now this also works in the empirical case, but it's stated just a little bit differently. An empirical case is where you perform an experiment many times. So under the equally likely assumption in an experiment, like if we were tossing a thumbtack, then if we wanted to know the probability that the thumbtack landed like point down, we would actually record the number of times that the thumbtack landed point down, and then we would divide it by the total number of times that we tossed the thumbtack. So in other words, an empirical probability, we would take the frequency that the event occurs divided by the total number of outcomes possible. In other words, the total number of times that I did the experiment. So in that case, we'd actually write it as f of e, where f stands for the frequency. So it would be the frequency of the event occurring over the number in the sample space. But they're really the same formula. Okay, now to understand the difference between theoretical and empirical probability, let's toss a single die, just a six-sided die. Now remember, casinos rely a great deal on the accuracy of a die. A fair die is very important to casinos because they rely on the probabilities. So they would expect, if you tossed a die, they would expect the probability of rolling each number 1 through 6. They would expect each of those probability to be 1/6. And that's the theoretical probability. But if we actually tested the die, let's say that we tested the die and we rolled, let's say we tossed the die 10,000 times with a machine, and let's say it came up, rolled a 1 3,000 times, a 2 1,000 times, a 3 1,000 times, a 4 3,000 times, a 5 2,000 times, and suppose we never got a 6 on it. Well, obviously that last one there would be a clue that something was off, because I think we would expect to get some 6s if we toss this die 10,000 times. But at any rate, then we could say that for this particular die, the probabilities are for a 1 would be 3,000 out of 10,000, which reduces to 3/10 or 0.3. For a 2 would be 1,000 out of 10,000, which is 0.1. Same thing for a 3, since we got 1,000 threes, so it'd be 1,000 out of 10,000, which is 0.1. And then for a 4, 3,000 out of 10,000 is 0.3. And then for a 5, we get 2,000 out of 10,000, which is 0.2. And then, of course, since we didn't get any 6s, the probability would be 0. Now, this is a acceptable probability assignment here if you actually use this, because the probabilities add up to 1. If you add these probabilities up, they all add up to 1, and they fall within the range from 0 to 1. So it would be acceptable, but obviously we would have some questions because these probabilities seem to be, several of them are a ways off from what they should be. Okay, so anyway, that's an example there. Now, so let's find some probabilities under the equally likely assumption. Suppose a pair of dice are tossed. Find the probabilities. Okay, so previously I gave you the 36 possible outcomes, and we know there's 36 because there's 6 ways to roll each dice, so it's 36 possibilities. The event of rolling a sum of 9. Well, to get a sum of 9, you can roll a 3-6, a 6-3, a 5-4, or a 4-5. So that's 4 ways to roll a sum of 9 out of 36. So the probability would be 4 out of 36, or 1/9. Now what about a sum of 7? Well, you can roll a 1-6, a 6-1, a 5-2, a 2-5, a 3-4, or 4-3. And so that means there's 6 ways to roll a sum of 7. So the probability would be 6 out of 36, which is 1/6. And then what about the event of rolling a sum of 2, 3, or 12? Well, in my event space, I had to list all the ways to roll a 2, which was just one way, 1 and 1. The ways to roll a 3, a 2, 1, and a 1, 2. And then the only way to roll a 12 is a 6, 6. So again, there's 4 ways out of 36 there. So that's 1/9. Now, if you actually play a game in the casino called craps, you'll find that 7 is an important number. And also the numbers 2, 3, and 12 are generally important numbers as well in certain instances. Okay, let me finish this video with a empirical example, and then we'll do some more examples on the next video. So suppose we have a survey of 1,000 drivers in a metropolitan area, and we asked them to fill out a form that asked how many accidents they had and also their ages. So suppose that we broke the age groups into 18 to 25, 26 to 39, 40 to 55, and 55 and older. And we asked them to tell us whether they've had 0 or 1 accidents, 2 to 3 accidents, or more than 3 accidents. And suppose these were the results. 100 people in the age group 18 to 25 said they had 0 to 1 accident. So 100 said that. 150 in the group 26 to 39 said they had 0 to 1 accidents, and so forth and so on. So now, based on the results, we can actually calculate the probability that if we select a random driver from this group, we can calculate the probabilities of certain things. So let's say we want the probability a driver will have more than one accident. Well, if you look at over here to the right, you see I've totaled each row. So the number of people that have 0 to 1 accidents, 575. The number of people that have 2 to 3 accidents would be 325. And the number of people that have more than 3 accidents is 325. So this 3 is 100, I'm sorry. This 325 has more than one accident, and these 100 have more than one accident. So all I have to do is add these together and get that 425 people out of 1,000 have more than one accident. So that's going to be 0.425. Now the next case is what's the probability the driver will be in the 26 to 39 category or have more than 3 accidents. Now this or right here is really like a union. So that's really a union there. So we're looking for the union of two sets. Now you may remember that when you want to calculate the union, you actually take the number that's in the first set, and then you add the number that's in the second set. And what was the second set? More than 3 accidents. So that would be this group. And so what you would do is you would actually add the number in this group, which is 200, and then add the number in this group, which is 100, and then subtract 25 so that you don't include it twice. So 200 plus 100 minus 25 is 275. So there's 275 in this category, and so that would be, probability would be 275 out of 1,000. Okay, and then a driver will be in the 40 to 55 category and have 0 to 1 accidents. Well, to be in that category, 40 to 55, and have 0 to 1 accident, we would be looking for where these two groups intersect. And so you can see that they intersect right here. You can see that they intersect right here at the 250. So this would actually be an intersection. And so that would be 250 out of 1,000, which is 0.25. And then if you wanted to know the probability of someone being in, say, the 26 to 39 group or the 40 to 55 group, well, notice there's no intersection for those two groups. So the addition principle tells me when there's no intersection, you can just add the totals together. So 200 plus 400 is 600, and so that's 0.6. And then here's an example of a complement, because it says a driver is not in the 55 plus range. Well, so let's take a look at how many are in the 55 plus range. Look, we have 100 people in the 55 plus range. So if we want to know the probability of selecting someone that's not, let's just subtract 100 from the total. So 100 from 1,000 is 900. So that means we have 900 that's not in that range. So therefore the probability would be 900 out of 1,000, which is 0.9. And so that's all I'm going to do on this video. So I'll do some more examples on the next.